What if something entered our solar system, moving so fast it defied the very laws of physics as we know them? That's not science fiction, it's the reality astronomers were confronted with when they identified an object now known as 3I Atlas, only the third confirmed interstellar visitor humanity has ever seen. But unlike its predecessors, the cigar-shaped ʻOumuamua that baffled scientists in 2017 or the icy comet Borisov discovered in 2019, this cosmic intruder was on another level entirely. Bigger, faster, and more active than anything we've encountered before, 3I Atlas is rewriting the rules of how objects travel between the stars. Imagine something potentially 24 kilometers across, dozens of times larger than Borisov, plunging into our solar system at 68 kilometers per second. That's fast enough to circle the Earth in under 10 minutes, or to travel from New York to Los Angeles in barely a minute and a half. Numbers like that don't just sound extreme, they break the models astronomers have used for decades to understand orbital motion and gravitational influence. An object moving that fast cannot be captured by the sun's pull. It can't be slowed down or held in orbit. Instead, it follows a hyperbolic trajectory, swinging around our star and then vanishing forever into the dark interstellar void, carrying its secrets away with it. And that's where the story turns even more urgent. We have only months to study this visitor before it disappears for eternity. The discovery of 3I Atlas begins like many astronomical breakthroughs, with an ordinary night at a telescope. On July 1, 2025, Larry Deno, a software engineer working at the Atlas Survey Telescope in Chile, was combing through routine images when he noticed a faint dot of light near Jupiter's orbit. At first glance, it looked like nothing special, just another minor blip among countless stars and asteroids. But the moment preliminary calculations were run, something didn't add up. This object wasn't moving like anything bound to the solar system. Its speed was so high, it made Deno's blood run cold. Within hours, observatories across the globe scrambled to confirm the sighting. Over 120 observations poured in within a single day, professional and amateur astronomers alike realizing they were witnessing something unprecedented. The designation came quickly, 3I Atlas. The 3I marking it as only the third interstellar object in human history, and Atlas honoring the telescope that first flagged it. But while the name gave it a place in the record books, what made Atlas unforgettable was what followed. Almost immediately, telescopes revealed it wasn't just a dead lump of rock passing silently through space. It was alive in the way comets are alive, sprouting a faint coma and an enormous tail tens of thousands of kilometers long. After countless millions of years drifting frozen through interstellar space, 3I Atlas was waking up under the sun's heat, shedding its ancient ices and dust, painting a streak across the sky as proof of its alien origins. For scientists, this was thrilling. For the public, it was shocking, because this wasn't some returning long-period comet from the Oort cloud. This was a true outsider, ejected from a distant star system long ago, and now passing us by chance. Even more unsettling, evidence emerged that Atlas had actually been visible in telescope archives weeks before its official discovery. It had been hiding in plain sight, camouflaged against the dense star fields of the Milky Way's galactic center, a region so crowded with light and dust that automated detection systems struggled to pick it out. Amateur astronomers combing through data uncovered images from mid-June, proving it had been there all along. This raised a chilling question. If such a massive interstellar comet could slip through undetected for weeks, how many others have we missed? What else is out there right now, invisible until too late? This is what makes 3I Atlas so extraordinary. It is not just another comet, it is a cosmic messenger, arriving from the depths of interstellar space, on a trajectory so extreme, it challenges everything we thought we knew. Its orbital eccentricity 6.2 is the most extreme path ever recorded. meaning it isn't just passing through, it's practically ignoring the sun altogether, barely nudged by gravity as it speeds on its way. Its speed, its size, its activity, and its mysterious chemistry all tell the story of catastrophic violence in another star system, where it was likely flung away by giant planets, binary stars, or even stellar explosions. And now it's here, giving us a brief, fleeting chance to study it before it vanishes forever. 3I Atlas is not just the biggest and fastest interstellar object ever discovered. It's a warning, a revelation, and perhaps the most important cosmic visitor humanity has ever encountered. On the night of July 1st, 2025, what began as routine work at the Atlas Survey Telescope in Chile turned into the kind of discovery that changes astronomy forever. Larry Deno, a software engineer accustomed to processing streams of observational data, was scanning through images that showed nothing unusual at first glance. The stars sat where they always did, the familiar pinpricks of light dotting the sky like a map etched into eternity. But then there was a faint, stubbornly moving point, a magnitude 18 speck drifting across the field. Such dots were not unusual in themselves. The telescope was designed to detect asteroids and comets that wander across the night sky, and most of them were harmless, catalogued and forgotten. But as Deno examined the calculations attached to this dot, his instincts told him something was off. The motion wasn't just fast, it was impossibly fast for something belonging to our solar system. The numbers suggested speeds reaching 68 kilometers per second relative to the Sun, a value so high that it immediately ruled out the possibility of it being a bound solar system object. For context, Earth orbits the Sun at about 30 kilometers per second, while even the fastest long-period comets barely touch 40. Nothing native to our solar system could naturally move at that speed and remain gravitationally tethered. Deno's pulse quickened. He later admitted that when he first saw the figures, his blood ran cold. The telescope hadn't just detected another rock. It had stumbled upon something alien, a true visitor from beyond the solar system. Within hours of that realization, astronomers worldwide were notified. The community responded at lightning speed, recognizing the potential magnitude of what had been found. By the following day, the Minor Planet Center had received over 120 independent observations from more than 30 observatories, both professional and amateur. The fact that such a faint, distant object could suddenly command global attention spoke to the rarity of what was unfolding. The designation soon followed, with the object officially named 3I Atlas on July 2nd. The 3I stood for the third interstellar object ever confirmed. After the enigmatic ʻOumuamua and the comet Borisov, Atlas, honoring the telescope that flagged it, would now carry the weight of history in its name. But while the designation placed it neatly in an astronomical record, what truly made this moment astonishing was what the early follow-ups revealed. Unlike ʻOumuamua, which baffled scientists with its cigar-like shape, lack of a tail, and unexplained acceleration, Atlas behaved like a comet almost immediately. Telescopes picked up signs of a faint coma, an expanding cloud of gas and dust surrounding its nucleus, as well as a tail stretching over 25,000 kilometers across space. This wasn't just a dead interstellar rock, silently coasting through the void. It was alive in the way comets are alive, responding to the heat of our sun by shedding ancient ice and dust that had lain dormant for millions or even billions of years. To astronomers, this meant an unprecedented opportunity. Atlas wasn't just a passerby, it was a messenger carrying chemistry from another planetary system, giving humanity a direct look at material forged around an alien star. And yet, for all the awe it inspired, the discovery also carried a sense of dread. The speed was so extreme, the trajectory so unbound, that scientists knew from the beginning this encounter would be painfully brief. Atlas was not staying. It had entered the solar system like a cosmic bullet. and within months, it would be gone forever, vanishing back into the endless dark between stars. That urgency made the July 1st detection feel like the opening of a race against time. Every hour lost meant data slipping away. Every night of poor weather or bad positioning meant secrets escaping beyond reach. This was not a visitor humanity could study leisurely. It was a fleeting miracle, and astronomers knew they had to mobilize instantly if they hoped to unlock its mysteries. The story of Atlas's discovery, then, is not just about a faint speck of light caught on a survey image. It is about the moment when the ordinary suddenly became extraordinary, when one engineer's sharp eye and routine diligence cracked open the door to another star system. It is about how quickly the scientific world can move when faced with the unimaginable, and most of all, it is about how the universe has a way of humbling us, reminding us that extraordinary visitors can appear at any time, carrying with them stories older and stranger than we can comprehend. July 1st, 2025 was the night humanity met its third confirmed interstellar guest. But it was only the beginning of a chain of revelations that would challenge not just astronomy, but our understanding of the cosmos itself. Confirmation came with stunning speed. And as astronomers digested the first wave of data, it became clear that this was no ordinary comet or asteroid wandering from the Oort cloud. The object's official designation, 3I Atlas, marked it as only the third interstellar visitor humanity has ever caught sight of. And its differences from its predecessors became evident almost immediately. ʻOumuamua, discovered in 2017, had been a puzzle wrapped in a mystery. A cigar-shaped body that showed no cometary activity, yet somehow accelerated in a way no natural explanation fully accounted for. Borisov, detected in 2019, provided more clarity by behaving exactly as one would expect an interstellar comet to behave, displaying an obvious coma and tail actively shedding ices as it passed near the sun. 3I Atlas, however, was not just a middle ground between those two. It was something entirely its own, combining the cometary behavior of Borisov with a scale and speed that dwarfed anything before it. Scientists watching the early observations couldn't help but marvel at how quickly it declared its alien identity. Almost as soon as telescopes were trained on it, 3I Atlas began to show off its cometary activity. Its coma, essentially the ghostly shroud of gas and dust surrounding its nucleus, was faint at first, but undeniably present. Then came the tail, stretching at least 25,000 kilometers across space, far longer than the Earth's diameter, proof that the sun's energy was awakening the frozen material buried deep inside its body. This behavior confirmed it wasn't just a rocky intruder, but a true comet, one that had likely formed in the cold outskirts of another planetary system before being violently ejected into the interstellar void. For astronomers, this was both thrilling and frustrating. Thrilling because it meant a direct sample of alien chemistry was suddenly within reach. Frustrating because the clock was already ticking. With its hyperbolic orbit, Atlas would only give humanity a brief glance before racing away forever. The designation itself carried a symbolic weight that set the stage for how astronomers approached it. To belong in the I category meant it was unbound, a traveler from beyond, and by becoming 3I Atlas joined a club so exclusive that each member had radically shifted the way science thought about interstellar space. ʻOumuamua had cracked open the door. Borisov had given the first taste of what such objects might look like, and now Atlas was throwing the door wide open, showing a scale and speed no one had dared expect. Already astronomers whispered that this could be the biggest interstellar object ever detected, possibly as large as 24 kilometers across, something on the order of a small moon. If true, it would dwarf Borisov by nearly 50 times in volume. But size wasn't the only thing that made Atlas remarkable. Its trajectory itself practically screamed alien. Unlike the neat elliptical orbits that define most solar system bodies, Atlas was on a hyperbolic path, one so open and extreme it barely seemed to notice the sun's pull. The numbers were staggering, an eccentricity of 6.2, the most extreme ever recorded. For context, anything above 1 is considered unbound and destined to leave the solar system. Earth's eccentricity is a neat 0.017. Halley's comet is 0.967, and even the wildest long-period comets rarely creep much above 1. Atlas's eccentricity was not just beyond the line, it was off the charts, so high it challenged the limits of orbital mechanics itself. Combined with its blistering 68 kilometers per second speed, Atlas wasn't just passing through. It was practically ignoring our sun, cruising on a path that made clear it came from far, far away. This combination of factors, its undeniable cometary activity, its immense size, its unparalleled speed, and its extreme trajectory made Atlas stand apart from ʻOumuamua and Borisov in ways no one had anticipated. Where ʻOumuamua had raised suspicions and questions, and Borisov had provided the first taste of normalcy in interstellar comet science, Atlas became a whole new category, a giant active comet hurtling through the solar system like a cosmic bullet. Scientists realized this was more than just a discovery. It was a once-in-a-generation opportunity to examine what planetary systems beyond our own are truly capable of producing. In many ways, Atlas was not just confirming that interstellar objects exist, it was revealing that the galaxy might be filled with them, that worlds out there were ejecting not just small fragments, but massive bodies capable of surviving the violence of their birth systems and traveling for millions of years across interstellar space. But as extraordinary as the confirmation was, what came next was even more unsettling. Astronomers digging into the archives quickly found that Atlas had been photographed before its official discovery, meaning it had been hiding in plain sight for weeks without anyone realizing what it was. This revelation would cast a shadow over the triumph of its detection, raising disturbing questions about just how prepared humanity really is to notice visitors from beyond before they slip away. What made the discovery of 3I Atlas even more dramatic was not just the speed with which it appeared, but the unsettling realization that the object had actually been hiding in plain sight long before its official announcement. In the immediate aftermath of the July 1st detection, astronomers began combing through archived data, searching for any trace of this alien visitor in earlier observations. To everyone's shock, amateur astronomers quickly discovered that Atlas had been photographed multiple times in the days and even weeks before Larry Dano flagged it at the Atlas telescope. Sam Dean, one of the first to dig into the archives from his home computer, stumbled upon images from late June, nearly a week before the discovery had been made public. There it was, the faint streak of light, perfectly visible against the backdrop of Sagittarius, moving in a way no background star could. And as more data poured in, it became clear this wasn't an isolated oversight. The Zwicky Transient Facility, another powerful sky survey, had also captured Atlas between June 14th and June 21st, weeks before the astronomical community realized what they were looking at. These early sightings extended the timeline of observation significantly, giving scientists a much clearer picture of its trajectory, but they also exposed an uncomfortable truth. NASA and other professional observatories had missed it, despite having the evidence right in front of them. The reason Atlas slipped through undetected lay in its unfortunate positioning. At the time, the comet was passing directly in front of the dense star fields of the galactic center. This region, located in the constellation Sagittarius, is the brightest and most chaotic portion of the night sky, home to billions of stars crammed into a relatively small region of space. Automated detection systems are trained to identify moving objects against relatively empty backdrops. They look for small points of light shifting slightly between frames. But against the backdrop of the galactic center, such movement is nearly impossible to distinguish. Imagine trying to pick out a single drifting snowflake in the middle of a blizzard. That was the challenge faced by the algorithm scanning the sky. The result was that Atlas passed almost invisibly across one of the worst possible regions for automated discovery, camouflaged among the billions of pinpricks of light. This near miss raised troubling questions. If a massive interstellar comet, potentially 24 kilometers across, could go unnoticed for weeks, how many others have slipped by completely undetected? Professor John Tondry from the University of Hawaii admitted that interstellar objects may be far more common than we realize, with quite a few passing through our solar system every year. The implication was staggering. If only 3 had been detected so far, ʻOumuamua, Borisov, and now Atlas, then humanity might have been missing countless others, simply because they didn't pass through the right part of the sky or weren't bright enough to catch our attention. The fact that Atlas was discovered at all felt almost like an accident, a cosmic stroke of luck that amateur persistence had salvaged from oblivion. These pre-discovery images also gave scientists a devastatingly precise trajectory for Atlas, confirming what the early calculations had hinted at: an orbital eccentricity of 6.2, the most extreme ever recorded. That number cemented Atlas's place as a true interstellar object, one so unbound by the sun's pull that it was essentially immune to our star's gravity. For astronomers, the expanded timeline was a blessing in disguise, allowing them to refine their models with far greater accuracy. But it also underscored just how fragile our detection systems are when faced with objects arriving from the stars. If this had been something more dangerous, an interstellar asteroid on a collision course instead of a comet passing harmlessly by, humanity might have had almost no warning at all. Amateurs like Sam Dean and Yaquan Z, who located even earlier traces in the Zwicky archives, became unlikely heroes in this unfolding drama. Their discoveries not only extended the timeline but also highlighted the glaring gap between professional resources and citizen science. While NASA's detection systems failed to flag Atlas early, individuals working from home computers pieced together the clues and revealed what the professionals had overlooked. This sparked debate across the scientific community about whether too much faith had been placed in automated systems and whether more emphasis should be given to human observation and cross-checking. After all, if the largest interstellar object ever detected nearly slipped away, what confidence could anyone have in our ability to spot smaller, faster, or more dangerous visitors? The revelation that 3i Atlas had been hiding in plain sight shifted the tone of the discovery from excitement to something more sobering. Yes, it was extraordinary to catch such a massive interstellar traveler, but the near miss also served as a warning about the limits of our cosmic awareness. It revealed vulnerabilities in our planetary defense systems and reminded us that the universe is filled with wanderers that do not wait for us to be ready. Atlas could so easily have been one of those that came and went unnoticed, leaving no trace but a mystery in old data files. The fact that it didn't slip away, that it was finally recognized and named, gave humanity a rare chance, but only for a short window, because even as astronomers celebrated uncovering its hidden history, the object was still racing through the solar system at impossible speed, and the clock was already counting down to the day it would vanish forever into interstellar space. The speed of 3i Atlas is what truly sets it apart and cements its reputation as one of the most extraordinary objects ever witnessed by astronomers. Traveling at a blistering 68 kilometers per second relative to the Sun, Atlas is moving at more than twice the velocity of any previously confirmed interstellar visitor. To put that into perspective, imagine circling the entire Earth in less than 10 minutes or flying from New York to Los Angeles in under 90 seconds. That is the scale of motion we are talking about. By comparison, ʻOumuamua, the mysterious, elongated object discovered in 2017, moved at 26 kilometers per second, while Borisov, the interstellar comet identified in 2019, traveled at about 32 kilometers per second. Both of those objects already shattered expectations, but Atlas makes them look almost sluggish. Its hyperbolic excess velocity, the speed it retains even when far from the sun's gravitational influence, measures around 60 kilometers per second. This means that not even the sun's powerful gravity can meaningfully slow it down. It came screaming into the solar system like a galactic bullet and will leave just as fast, on course to vanish into the interstellar void forever. What makes this velocity so astounding is that it far exceeds the escape velocity of our solar system. Typically, objects bound to the sun's gravity move at speeds less than 45 kilometers per second depending on their distance from the star. Atlas surpasses that threshold by a huge margin, proving that it is not a solar system native. Such speeds cannot be explained by the normal mechanics of an orbit. They demand an origin story rooted in catastrophic events far beyond our neighborhood. The prevailing theory is that Atlas was violently ejected from its home planetary system through gravitational interactions so extreme they defy imagination. A massive planet, perhaps a gas giant many times the size of Jupiter, could have slingshotted the comet outward during a period of orbital instability. Alternatively, a close pass by a neighboring star might have yanked it free, hurling it into interstellar space with tremendous force. Even more dramatic possibilities exist. Binary star systems, with their chaotic three-body dynamics, or even the asymmetric blast of a nearby supernova, could provide the kind of cosmic violence necessary to accelerate an object to such velocities. Regardless of the specific cause, the message is clear. Atlas has survived an encounter with some of the most violent forces in the galaxy. What astonishes scientists even more is that despite these forces, the comet remained intact. Smaller or weaker objects would have been torn apart by such violent ejections, but Atlas endured, suggesting that its nucleus is both large and structurally resilient. Early size estimates placed it at possibly 24 kilometers across, though later refinements suggest it may be smaller in the range of 5 to 15 kilometers. Even at the lower end of this estimate, its sheer bulk is impressive, making it far larger than ʻOumuamua and Borisov. Coupled with its velocity, this makes Atlas a cosmic missile unlike anything we have ever observed. The implications of such speed extend far beyond curiosity. It fundamentally challenges our models of how frequently interstellar visitors pass through our solar system. If Atlas achieved its velocity through natural means, then there must be countless others like it, cosmic debris flung into the galaxy by violent gravitational encounters. If, on the other hand, objects this fast are rare, then perhaps we were unimaginably lucky to witness one at all. Either way, its presence raises profound questions about how many such travelers are currently racing unnoticed through our solar system, too faint or too fast for us to detect. The fact that Atlas was only recognized thanks to amateur scrutiny of archival images underscores the fragility of our observational systems. The comet's incredible speed also places severe constraints on how long we have to study it. Moving at 68 kilometers per second, Atlas is here for only a fleeting window. In astronomical terms, it is the blink of an eye. The comet will reach perihelion, the closest point to the Sun, on October 29, 2025, at just inside the orbit of Mars. By early December, it will already be fading from view, headed back into the interstellar abyss. This urgency has created a frenzy among astronomers worldwide, with observatories scrambling to secure telescope time before the object is lost forever. The James Webb Space Telescope, with its unparalleled infrared capabilities, is expected to play a central role in analyzing Atlas's composition and structure. But even Webb will only have a short window to work with. Once Atlas vanishes into the darkness, humanity's chance to study it is gone for good. Ultimately, the speed of 3I Atlas is not just a number, it is a story written in motion. It tells us of violent ejections in alien systems, of a journey spanning millions or even billions of years, of survival through the coldest and most hostile regions of interstellar space. It is a reminder that the universe is not, if the staggering speed of 3I Atlas seemed almost beyond comprehension, its orbital eccentricity pushed the mystery even further into uncharted territory. Astronomers measure orbits using a parameter called eccentricity, which essentially describes how stretched out or elongated a path is. A perfect circle has an eccentricity of 0, while Earth's orbit, nearly circular, has a value of 0. Even highly elongated orbits, such as that of Halley's comet with its 76-year cycle, only reach about 0.967. Once eccentricity exceeds 1, the path is no longer a closed loop, but instead becomes hyperbolic, meaning the object is not bound to the Sun at all and will pass through our solar system once before escaping forever. Both ʻOumuamua and Borisov had eccentricities just above 1,000, consistent with interstellar trajectories. But 3I Atlas shattered that precedent, clocking in with a mind-bending eccentricity of 6.2, the most extreme trajectory ever recorded for any object passing through our cosmic neighborhood. To appreciate how unusual this number is, imagine drawing the orbits of Earth, Mars, and comets, like Halley's on paper. They are all elongated ovals that eventually close back on themselves. Even the long-period comets, with orbits stretching out tens of thousands of years, would still loop back after their journeys. But when the eccentricity goes above 1, the oval never closes. It stretches into an open curve that shoots through the solar system like a slingshot and never returns. Now, take that curve and stretch it to the extreme, flattening it so far it barely bends at all, almost like a straight line passing near the Sun. That is what an eccentricity of 6.2 represents. It means Atlas was moving so fast that the Sun's gravity could barely alter its trajectory. Even at perihelion, when it passed closest to our star, the comet's path was hardly deflected. The Sun, which governs the fates of planets, moons, and comets within billions of kilometers, could do little more than brush its path ever so slightly before it sped away again. This extreme orbital eccentricity not only proved that Atlas was interstellar, but also hinted at the violence of its past. To achieve such an open trajectory, the comet had to be hurled from its home system with extraordinary force, more than any gentle nudge from planetary migration could provide. Astronomers theorize that binary stars, giant planets in chaotic motion, or even a supernova explosion in the comet's original neighborhood could have supplied the energy. In all cases, the number 6.2 encodes a history of destruction and upheaval, a cosmic environment where gravitational forces ripped apart normal orbits and flung debris out into the galaxy at record-breaking speeds. What troubled astronomers even more was the implication that if one object could achieve such an eccentricity, perhaps there were countless others. The galaxy might be filled with these hyperbolic wanderers, zipping silently between stars on paths so extreme that they rarely encounter another system, let alone one with intelligent observers ready to study them. And yet, here was Atlas, by pure chance, cutting across the solar system in 2025, offering a fleeting glimpse into that hidden population. It was like catching sight of a single drop of water flung from a distant storm, a messenger carrying secrets from worlds that may no longer even exist. The mathematics of Atlas's orbit also raised philosophical questions. Astronomers are used to dealing with predictable systems, elliptical orbits that repeat, cycles that can be forecast centuries ahead. Atlas defied that comfort. Its eccentricity was so large that normal orbital dynamics seemed almost irrelevant. It was, for all intents and purposes, on a straight-line journey through space, merely brushing past our solar system on its way elsewhere. That realization forced scientists to rethink what orbital dynamics might look like in extreme environments. Could there be a whole class of objects with eccentricities this high, lurking just beyond the edge of detectability? If so, what does that say about the violent birth and death of planetary systems across the galaxy? Perhaps the most chilling part of Atlas's eccentricity was what it revealed about our own vulnerabilities. The comet's trajectory happened to pass harmlessly through, but if an object with a similar eccentricity and mass were on a collision course with Earth, detection might come too late. Its speed and trajectory would leave little room for intervention. The discovery that Atlas had been hiding in archived data for weeks before recognition already raised alarms. Coupled with its eccentricity, it was a stark warning that our ability to track interstellar threats is far from complete. The universe does not guarantee that the next visitor will simply pass by. For now, though, the eccentricity of 3I Atlas remains a scientific gift, a number that forces researchers to confront the limits of their models and compels them to seek new explanations. It is a mathematical fingerprint of violence written into the trajectory of a wandering comet, a reminder that our galaxy is a dynamic, chaotic place where destruction is as common as creation. And as extraordinary as that number is, it was only the beginning of the story. Because Atlas was not just a mathematical curiosity, it was a physical body, a nucleus shedding gas and dust, and what those emissions revealed about its composition promised to shake our understanding of interstellar chemistry to its core. A calm or predictable place, but a theater of chaos and violence, where worlds are born, destroyed, and cast adrift. Atlas carries that story with it as it streaks past our sun, a fleeting messenger from a distant corner of the galaxy. And as scientists scramble to decode its secrets before it disappears forever, they are left with a sobering truth. This cosmic bullet challenges everything we thought we knew about the speed, strength, and abundance of interstellar wanderers. If the staggering speed of 3I Atlas seemed almost beyond comprehension, its orbital eccentricity pushed the mystery even further into uncharted territory. Astronomers measure orbits using a parameter called eccentricity, which essentially describes how stretched out or elongated a path is. A perfect circle has an eccentricity of 0, while Earth's orbit, nearly circular, has a value of 0.017. Even highly elongated orbits, such as that of Halley's comet with its 76-year cycle, only reach about 0.967. Once eccentricity exceeds 1, the path is no longer a closed loop, but instead becomes hyperbolic, meaning the object is not bound to the sun at all and will pass through our solar system once before escaping forever. Both ʻOumuamua and Borisov had eccentricities just above 1 Tharn, consistent with interstellar trajectories. But 3I Atlas shattered that precedent, clocking in with a mind-bending eccentricity of 6.2, the most extreme trajectory ever recorded for any object passing through our cosmic neighborhood. To appreciate how unusual this number is, imagine drawing the orbits of Earth, Mars, and comets like Halley's on paper. They are all elongated ovals that eventually close back on themselves. Even the long-period comets, with orbits stretching out tens of thousands of years, would still loop back after their journeys. But when the eccentricity goes above 1, the oval never closes. It stretches into an open curve that shoots through the solar system like a slingshot and never returns. Now take that curve and stretch it to the extreme, flattening it so far it barely bends at all, almost like a straight line passing near the sun. That is what an eccentricity of 6.2 represents. It means Atlas was moving so fast that the sun's gravity could barely alter its trajectory. Even at perihelion, when it passed closest to our star, the comet's path was hardly deflected. The sun, which governs the fates of planets, moons and comets within billions of kilometers, could do little more than brush its path ever so slightly before it sped away again. This extreme orbital eccentricity not only proved that Atlas was interstellar, but also hinted at the violence of its past. To achieve such an open trajectory, the comet had to be hurled from its home system with extraordinary force, more than any gentle nudge from planetary migration could provide. Astronomers theorized that binary stars, giant planets in chaotic motion, or even a supernova explosion in the comet's original neighborhood could have supplied the energy. In all cases, the number 6.2 encodes a history of destruction and upheaval, a cosmic environment where gravitational forces ripped apart normal orbits and flung debris out into the galaxy at record-breaking speeds. What troubled astronomers even more was the implication that if one object could achieve such an eccentricity, perhaps there were countless others. The galaxy might be filled with these hyperbolic wanderers, zipping silently between stars on paths so extreme that they rarely encounter another system, let alone one with intelligent observers ready to study them. And yet, here was Atlas, by pure chance cutting across the solar system in 2025, offering a fleeting glimpse into that hidden population. It was like catching sight of a single drop of water flung from a distant storm, a messenger carrying secrets from worlds that may no longer even exist. The mathematics of Atlas's orbit also raised philosophical questions. Astronomers are used to dealing with predictable systems, elliptical orbits that repeat, cycles that can be forecast centuries ahead. Atlas defied that comfort. Its eccentricity was so large that normal orbital dynamics seemed almost irrelevant. It was, for all intents and purposes, on a straight-line journey through space, merely brushing past our solar system on its way elsewhere. That realization forced scientists to rethink what orbital dynamics might look like in extreme environments. Could there be a whole class of objects with eccentricities this high, lurking just beyond the edge of detectability? If so, what does that say about the violent birth and death of planetary systems across the galaxy? Perhaps the most chilling part of Atlas's eccentricity was what it revealed about our own vulnerabilities. The comet's trajectory happened to pass harmlessly through, but if an object with a similar eccentricity and mass were on a collision course with Earth, detection might come too late. Its speed and trajectory would leave little room for intervention. The discovery that Atlas had been hiding in archived data for weeks before recognition already raised alarms. Coupled with its eccentricity, it was a stark warning that our ability to track interstellar threats is far from complete. The universe does not guarantee that the next visitor will simply pass by. For now, though, the eccentricity of 3I Atlas remains a scientific gift, a number that forces researchers to confront the limits of their models and compels them to seek new explanations. It is a mathematical fingerprint of violence written into the trajectory of a wandering comet, a reminder that our galaxy is a dynamic, chaotic place where destruction is as common as creation. And as extraordinary as that number is, it was only the beginning of the story, because Atlas was not just a mathematical curiosity, it was a physical body, a nucleus shedding gas and dust, and what those emissions revealed about its composition promised to shake our understanding of interstellar chemistry to its core. If the speed and orbital eccentricity of 3I Atlas were enough to shock astronomers into rethinking the mechanics of interstellar wanderers, its physical nature and composition only deepened the mystery. Almost immediately after telescopes began to focus on the object, signs of cometary activity emerged. Unlike ʻOumuamua, which remained frustratingly inactive and sparked wild speculation about its origins. Atlas behaved much more like a traditional comet, though on a scale that felt extraordinary. Astronomers detected a faint but distinct coma surrounding its nucleus, a shroud of gas and dust released as solar radiation began to warm its icy surface after millions of years, drifting in frozen darkness. Soon after, images revealed a diffuse tail stretching tens of thousands of kilometers through space, a glowing banner that marked Atlas as very much alive. This activity wasn't just a spectacle, it was a priceless scientific opportunity. Every molecule released from its surface represented ancient material, preserved since the object's formation in an alien star system, offering humanity its first direct sample of chemistry from beyond our sun. What made Atlas stand out further was the distinctive reddish hue of its coma and tail. Observations from telescopes in Hawaii and the Canary Islands revealed a coloration strongly indicative of complex organic molecules embedded within the dust grains. This was no ordinary cometary dust, but material enriched with hydrocarbons and other carbon-based compounds, the very precursors of life as we know it. The similarity to the previously studied interstellar comet Borisov was striking, suggesting that the processes that create organic-rich comets may be common across planetary systems. To many scientists, this was the most profound revelation of all. The chemistry necessary to build life is not unique to our solar system, but is scattered freely throughout the galaxy, carried on the backs of wandering comets like Atlas. Spectroscopic analysis added even more depth to the picture. Instruments capable of breaking down the light emitted by the coma revealed the presence of water vapor, carbon monoxide, carbon dioxide, and traces of methane and ammonia. These are the same volatile compounds found in comets native to our solar system, but their ratios and abundances hinted at subtle differences in the conditions of Atlas's birth environment. Some of the chemical fingerprints pointed to formation in the frigid outer reaches of its parent system, where ices can remain stable for billions of years. Others suggested mixing processes that might have transported material inward and outward, just as occurred in our own early solar system. Each reading was like a puzzle piece, offering tantalizing clues about the star system that once gave rise to this cosmic traveler. The dust particles escaping from Atlas also provided invaluable information. By studying how the coma scattered light at different wavelengths, astronomers could estimate the size distribution of the grains. Larger, denser particles implied recent activity from the nuclear surface, while smaller, finer grains likely represented ancient material altered by cosmic radiation during the object's interstellar journey. The fact that both types were present suggested that Atlas's core was complex and layered, with fresh ices exposed alongside ancient crusts hardened by eons of exposure to radiation. This duality hinted at the incredible resilience of its nucleus, which had survived millions of years of bombardment by cosmic rays, only to awaken spectacularly when bathed in sunlight once more. Beyond the science, there was also the sheer awe of it. Every observation of the reddish glow and streaming tail reminded astronomers and the public alike that this was not just another comet, it was a messenger from a place we may never see, carrying within it a story billions of years old. If comets like Atlas are common in the galaxy, then perhaps so too are the building blocks of life, waiting for the right conditions to spark into complexity. The possibility that such objects could seed life across planetary systems, delivering organics wherever they wander, was no longer a fringe theory, but a compelling narrative supported by direct evidence. And yet, Atlas's activity also raised urgent challenges. Its coma and tail made it brighter and easier to observe, but they also complicated efforts to determine the true size of its nucleus. Was it a massive 20-kilometer wide giant or a smaller body hidden beneath a dazzling cloak of dust and gas? Opposition surge effects, where sunlight reflects directly back from dust particles, made brightness measurements even more misleading. Astronomers struggled to disentangle the glow of the coma from the light of the nucleus itself, leaving estimates uncertain. But regardless of its precise size, the fact remained: Atlas was one of the most active, most chemically rich interstellar visitors ever detected, and the clock was ticking to study it before it vanished forever. Its composition carried implications not just for science, but for our place in the cosmos. The organics, the water, the ammonia, all of it pointed to a simple truth: the ingredients for life are not confined to Earth, or even to our Sun's family of planets. They are scattered across the galaxy, preserved in icy vaults, and delivered by comets like Atlas. Each observation of its reddish coma was a reminder that the story of life may be written on a cosmic scale, with wanderers like this carrying chapters from one star system to another. And as Atlas raced toward perihelion, flaring brighter by the day, astronomers knew they were witnessing something both ancient and fleeting, a chemical message from the stars that would soon be gone forever. The survival of 3I Atlas across its unimaginable journey through interstellar space may be its most astonishing feature, because everything about the environment it has traveled through for millions or even billions of years should have destroyed it long before it reached our solar system. Space between the stars is a realm of extremes. Temperatures plummet to nearly absolute zero, hovering around 270 degrees Celsius, while high-energy cosmic rays race through the void, constantly bombarding any object in their path with radiation powerful enough to shatter molecules and alter atomic structures. Yet Atlas endured, and when it came within reach of our telescopes, it revealed itself not as a dead, inert rock, but as a living comet, active, releasing gas and dust, its nucleus intact. That resilience forces us to consider just how tough and ancient interstellar objects truly are, and what stories they can preserve from their long exile. One factor in Atlas's survival is the creation of a protective crust during its journey. As cosmic rays pelted the comet's outer layers, they broke down molecules, altering chemical bonds and producing a hardened, irradiated shell. This outer crust acted like armor, shielding the more delicate ices and compounds deeper within from further damage. When the comet finally encountered the warmth of our sun, this protective layer began to crack, exposing fresh material that had been sealed off from the destructive forces of deep space. That is why its activity appeared vigorous despite its long journey. The gases it released were not the fragile remnants of a decayed surface, but pristine ices that had remained untouched for eons. It is almost as if Atlas carried with it a time capsule, a chemical fingerprint from the moment of its formation, hidden beneath a hardened shell, until this fleeting encounter with the solar system. Cosmic radiation should have also obliterated much of its organic chemistry, yet Atlas still displayed strong signatures of complex hydrocarbons. This suggests that even in the most hostile environments, organic molecules are more resilient than once believed. Laboratory experiments on Earth have shown that certain organics can survive bombardment by high-energy particles if buried just a few centimeters below the surface. Atlas seems to confirm this at a cosmic scale. Despite constant exposure to radiation across millions of years, it retained compounds that may resemble the very building blocks of life. The discovery supports the provocative idea that interstellar comets could act as carriers of prebiotic material across star systems, seeding planets with the raw ingredients necessary for life. If Atlas endured intact for so long, then perhaps countless other objects like it are quietly transporting organic chemistry throughout the galaxy. The extreme cold of interstellar space also played a paradoxical role in preserving the comet. At temperatures so low that atomic motion nearly ceases, most chemical reactions simply stop. While radiation was altering the outer layers, the deep interior remained inert, frozen in a kind of suspended animation. This is why, when warmed by sunlight, Atlas responded with such vigor. It was not a withered husk, but a frozen archive suddenly reawakened. Its long dormancy preserved volatile compounds like water, methane, and ammonia, which would have evaporated long ago in less extreme conditions. In a strange way, the very harshness of interstellar space ensured the comet's survival, keeping its ancient cargo of ices and organics sealed and stable for a journey longer than humanity itself has existed. The sheer structural integrity of Atlas is also remarkable. Smaller, weaker objects are far more likely to disintegrate during ejection from their home systems or during the long battering they receive while traveling between stars. Atlas's survival implies that its nucleus is large and mechanically strong, with gravity sufficient to hold it together against the stresses of violent ejection and constant radiation. This may explain why it is significantly larger than previous interstellar visitors like ʻOumuamua or Borisov. Only the biggest and most robust objects can endure such journeys intact. Its survival is proof of the galaxy's harsh filtering process. Countless smaller fragments are surely destroyed, but those that survive become messengers, carrying with them preserved chemistry from long-dead systems. What makes Atlas's survival especially compelling is how it forces us to think about panspermia, the hypothesis that life's building blocks, or even microbial life itself, could travel between stars aboard comets and asteroids. If Atlas can preserve complex organics through millions of years in the deep freeze of interstellar space, could it also preserve more delicate molecules or even dormant biological structures? While no evidence suggests Atlas carries life, the possibility that such objects might act as delivery systems cannot be ignored. In fact, the very resilience it has demonstrated lends weight to the idea that the galaxy could be interconnected by a steady trickle of cometary couriers, each one carrying fragments of chemistry from one planetary system to another. Atlas's endurance is therefore not just a curiosity, it is a revelation. It shows that interstellar comets are not fragile flukes, but resilient survivors capable of preserving secrets from across the galaxy. Every molecule released from its coma now is a survivor's tale, proof that the galaxy is not empty but alive with travelers that have seen more than we can imagine. And as astronomers raced to capture its emissions before it disappeared forever, they knew that what they were studying was not just a comet but a record of survival written in ice and dust, a story of endurance across the most brutal environment in the universe. If there was one aspect of 3I Atlas that truly shook astronomers, it was the question of how it achieved its catastrophic ejection from its home system with such extreme velocity. An event so violent it transformed an ordinary comet into a galactic wanderer traveling faster than anything we had ever seen before. Objects do not reach 68 kilometers per second relative to the Sun by accident, nor do they achieve orbital eccentricities of 6.2 without a cosmic upheaval of staggering proportions. The trajectory of Atlas is a fossilized trace of an ancient disaster, a celestial crime scene etched into mathematics, and unraveling it forces us to imagine the kinds of violent forces that tear apart planetary systems and fling debris across interstellar space. One of the most likely scenarios is interaction with a giant planet. In our own solar system, Jupiter's enormous gravity has ejected countless comets into distant regions like the Oort cloud, and in rare cases has even hurled them completely out of the Sun's grasp. If Atlas formed in the outer reaches of another system, a close encounter with a massive planet could have accelerated it to interstellar speeds. But Atlas's extreme velocity suggests something more dramatic than a simple slingshot, perhaps multiple encounters with more than one giant planet, or a system where planets themselves were migrating chaotically, disrupting everything in their path. Simulations of planetary migration show that when massive planets shift their orbits, they can destabilize entire belts of comets, sending thousands flying outward like cosmic shrapnel. Atlas may be one of those unlucky fragments, a survivor cast into the abyss by a gravitational catastrophe. Another possibility involves binary stars, which are common in the galaxy. If Atlas originated in a system with two suns orbiting one another, its path could have been altered by complex three-body interactions. Objects caught between two massive stars can experience chaotic gravitational kicks that accelerate them to extraordinary speeds before ejecting them permanently. The retrograde inclination of Atlas's orbit relative to our solar system suggests that such interactions might be at play. Because retrograde trajectories often point to highly chaotic histories, in such a system, Atlas could have spent millions of years on a stable orbit before one violent encounter launched it into interstellar exile. Even more dramatic are the possibilities involving stellar deaths. When a massive star ends its life in a supernova explosion, the shockwaves and gravitational asymmetries can hurl nearby objects outward at astonishing speeds. Though Atlas is not moving anywhere near the fraction of light-speed velocities that supernovae can generate, it is plausible that some distant but catastrophic stellar event imparted just enough force to knock it free of its system. A less extreme but still violent mechanism involves close passes between star systems. If two stars wander close enough, their gravitational fields can tug on one another's outer regions, stripping comets and asteroids away like thieves stealing from each other's vaults. In such encounters, comets are often tossed into deep space with trajectories like Atlas's, doomed to wander forever. What makes Atlas particularly fascinating is that its trajectory seems to point back toward the dense region of Sagittarius, near the galactic center where the stellar environment is especially violent. In those crowded neighborhoods, stars are packed tightly together, and encounters between systems happen far more frequently than in the quieter suburbs where our sun resides. Planetary systems born in such chaotic zones may be prone to losing their comets and asteroids to interstellar space at far higher rates, producing a steady stream of wanderers like Atlas. If this is true, then what we are seeing is not an isolated fluke, but the inevitable result of galactic dynamics, with the central regions of the Milky Way acting as factories for interstellar debris. Atlas's ejection, then, is not merely a personal tragedy of a comet losing its home, but a revelation about the violence inherent in cosmic evolution. Planetary systems are not always stable, serene places. They are battlegrounds where gravity decides winners and losers. Some worlds survive and thrive, while others are scattered into darkness. Atlas represents the losers of that lottery, a piece of planetary raw material expelled into eternal exile. But from a human perspective, its exile is our opportunity, for in being cast out, it brought with it a chemical record of its home system, preserved in ice and dust, and delivered to our telescopes in the narrow window of its visit. The violence that ejected Atlas also forces us to reconsider how common such objects might be. If every planetary system goes through chaotic phases, planets migrating, stars passing near one another, supernovae detonating, then every system is likely producing its own exiles, countless trillions of objects like Atlas flung into the galaxy. The implication is staggering. Interstellar comets and asteroids may be far more common than we thought, wandering the galaxy in endless numbers, most of them unseen. Atlas is just one that happened to cross our path, but it represents a vast, unseen population of cosmic refugees traveling between the stars. In that sense, Atlas is both a survivor and a casualty. It is proof that planetary systems are violent places, but also proof that even in the chaos, fragments endure. It shows us that the galaxy is not static, but restless, constantly reshaping itself in cycles of creation and destruction. And while its ejection may have been catastrophic in its home system, here in ours, it has become a priceless gift carrying a story of violence that spans millions of years and millions of light years of travel, a reminder that the universe is a place where even the smallest bodies are forged in fire and flung into infinity. For every interstellar visitor like 3I Atlas that we manage to detect, astronomers suspect there are countless others slipping through the solar system completely unnoticed. A silent traffic of cosmic wanderers weaving between the planets without ever being recognized. The discovery of Atlas was almost a near miss itself, hidden for weeks in the crowded star fields of Sagittarius, where its faint glow was camouflaged against billions of background stars. It was only by luck and persistence that amateur astronomers went back through archived images and found evidence of its passage before professional teams officially confirmed it. This revelation exposed not just the uniqueness of Atlas, but a far more troubling truth. Our detection systems are blind to much of what passes through the solar system, and the population of interstellar objects may be larger and more diverse than we ever dared to imagine. Astronomers like John Tonry of the University of Hawaii have admitted that quite a few interstellar visitors likely pass through our inner solar system every year. The problem is not that they aren't there, it's that they're too faint, too small, or passing through inconvenient regions of the sky where detection algorithms struggle. Most surveys are optimized to find near-Earth objects, asteroids and comets, with predictable trajectories against relatively uncluttered backgrounds. When an object like Atlas comes in from a direction filled with stars, or when it shines at magnitude 18, barely above the limits of many telescopes, it becomes a needle in a cosmic haystack. The fact that amateurs could spot it in data after the fact shows that our technology is capable, but our systems are overwhelmed, and many interstellar wanderers are simply slipping past us. Statistical models built from the 3 confirmed interstellar objects, ʻOumuamua, Borisov and Atlas, suggest a hidden population numbering in the trillions across the galaxy. If every planetary system ejects countless comets and asteroids during its violent early history, then interstellar debris should be everywhere, drifting through space in an endless diaspora. Most are small, only meters or tens of meters across, and would only reveal themselves if they came very close to Earth, glowing faintly or streaking through the atmosphere as meteors. Others, like Atlas, are far larger and brighter, but still manage to evade detection until they are already deep inside the solar system. The uncomfortable implication is that our picture of interstellar visitors is shaped not by what exists, but by what our limited tools happen to catch. The near miss with Atlas also highlights a glaring vulnerability in planetary defense. If a comet tens of kilometers across could remain hidden for weeks simply because it was moving against a bright background, what other potential threats are slipping past unseen? While Atlas poses no danger, it will never come close enough to Earth. Its discovery revealed a flaw in our surveillance net. Automated detection systems, designed to scan for dangerous asteroids, can fail in regions of high star density or when objects approach from the direction of the sun. That means the most dangerous comets, those arriving on steep, fast trajectories from interstellar space, could be the ones we are least prepared to detect. Atlas is a reminder that our cosmic blind spots are real and potentially costly. And yet, these failures also open doors. The fact that Atlas was found at all shows that our detection capabilities are improving, and with upcoming facilities like the Vera C. Rubin Observatory, the odds of catching more interstellar visitors are set to rise dramatically. Rubin's ability to scan the entire sky every few nights with its massive 3.2 gigapixel camera promises to turn rare discoveries into routine science. Astronomers predict that once it comes online, we may detect up to 10 interstellar objects every year. With each detection, we gain not just another comet or asteroid, but another data point in the great cosmic experiment of planetary system formation, each one carrying information about chemistry, dynamics, and the violent histories of alien worlds. Atlas itself represents the tip of a vast iceberg. Its discovery proves that the galaxy is littered with exiles, fragments of planetary systems long dismantled or disrupted. Some may come from systems with gas giants like Jupiter, others from binary stars, and still others from places where supernovae scattered debris like shrapnel. Each one carries a story written in its trajectory and composition, and together they could form a galactic library of planetary history. But for now, we have only a handful of volumes in that library, and most of its shelves remain hidden in the dark. The realization that trillions of such wanderers might exist forces us to reconsider our place in the galaxy, not as isolated observers, but as part of a cosmic crossroads where material from distant stars regularly passes by. The hidden population of interstellar objects is both humbling and inspiring. It humbles us because it shows how little of the universe we actually see, how vast the galaxy's movements are compared to our narrow observations. It inspires us because it means we are not cut off from the rest of the galaxy. Alien materials visit us, carrying with them secrets of systems we may never otherwise touch. Each detection is a chance to sample a different corner of the galaxy without leaving home. Atlas is not just one comet. It is a messenger reminding us that our solar system is part of a much larger flow of cosmic material, a galactic circulation that binds stars and planets together across light years. The timeline of 3I Atlas's passage through our solar system offers astronomers one of the most thrilling opportunities ever presented by an interstellar object, a chance to observe it up close as it swings around the Sun and makes a near pass of Mars before vanishing forever into the depths of interstellar space. This brief window is our only opportunity to study its activity as it awakens under solar heating, its chemical composition as fresh material is released, and its structural integrity as it endures forces that will test it to the limit. Every moment of its trajectory is precious, and the approach toward perihelion, the closest point to the Sun, represents the climax of this cosmic event. On October 29, 2025, Atlas will reach a distance of 1.356 astronomical units from the Sun, placing it just inside the orbit of Mars. This proximity is close enough to trigger massive sublimation of its frozen interior, forcing gases, dust, and potentially even large chunks of material into space, all of which can be analyzed by telescopes on Earth and in orbit. For astronomers, this is the equivalent of opening a sealed time capsule from another star system. But before it reaches perihelion, Atlas will stage an even more extraordinary encounter, its close flyby of Mars on October 3rd. At a distance of just 29 million kilometers, this approach will allow the planet's fleet of orbiters to turn their instruments toward it, capturing details that Earth-based telescopes could never hope to resolve. The Mars Reconnaissance Orbiter, with its powerful HiRISE camera, could potentially capture images of the nucleus itself, resolving surface structures, jets of gas, and the formation of cracks as solar heating intensifies. Instruments aboard MAVEN, designed to study the Martian atmosphere, can instead turn to measure the gases escaping from Atlas, while the European Space Agency's Mars Express can use its infrared spectrometers to probe its composition. These spacecraft, stationed by coincidence in the perfect vantage point, will essentially act as interstellar comet observers, giving humanity its closest ever look at a visitor from beyond the solar system. From Mars's perspective, Atlas may brighten to an apparent magnitude of 11, making it an easy target for orbital instruments. The scientific value of these observations cannot be overstated. They will represent the first time interstellar material has been studied at such close range, bridging the gap between distant telescope data and direct spacecraft encounters. For observers on Earth, however, the timing is bittersweet. When Atlas reaches perihelion on October 29th, Earth will be positioned on the opposite side of the Sun, effectively blocking us from direct observation of its most active phase. From our vantage point, the comet will be hidden in solar glare, impossible to study with ground-based telescopes during its peak outgassing. This creates a sense of urgency. Astronomers must capture as much data as possible before the comet disappears into the blinding light of the sun, because by the time it re-emerges in December, it will already be on its outbound journey, dimmer, less active, and moving away at extreme speed. The months leading up to perihelion will therefore be critical, a global scramble to collect as much information as possible before the opportunity vanishes forever. The sun's energy at perihelion will play a decisive role in revealing Atlas's true nature. As the comet heats, ices buried deep within its nucleus will sublimate, producing jets and streams of gas that expand into its coma and tail. Spectroscopic analysis of these emissions will identify the molecular building blocks it carries, including water vapor, carbon monoxide, carbon dioxide, methane, and complex organic compounds. Each of these chemical fingerprints represents material formed in an alien planetary system billions of years ago, preserved and now released for our instruments to decode. For scientists, perihelion is not just a fiery spectacle, but a rare chance to directly sample the chemistry of another world's debris, a laboratory experiment billions of years in the making. The closest approach to Mars adds another layer of intrigue, because it provides two unique perspectives. The global telescope network on Earth, observing from afar, and spacecraft around Mars capturing it from relatively close range. This stereoscopic approach will allow scientists to build three-dimensional models of its coma and tail, mapping how material is released and how it interacts with the solar wind. The Mars flyby could also offer subtle gravitational insights. By tracking tiny deviations in the comet's path as it passes Mars, scientists can refine estimates of its mass and density, critical for understanding whether it is a loosely bound rubble pile or a solid, monolithic object. These questions are fundamental for interpreting not only Atlas itself, but also the wider population of interstellar visitors. Yet, there is a sense of tragedy in this opportunity. For all the sophistication of our telescopes and spacecraft, Atlas is already on its way out, and nothing we do can slow it down. Its perihelion is not a turning point, but a farewell, a final flare of activity before it disappears into the void. Unlike solar system comets, which return after decades or centuries, Atlas will never come back. Its hyperbolic trajectory ensures that after this brief encounter, it will be gone forever, carrying its secrets beyond our reach. This makes the Mars encounter and perihelion not just scientific opportunities, but historic events, milestones in our effort to understand interstellar messengers. Every observation counts. Every photon of light captured a clue in deciphering its alien origins. The passage of Atlas reminds us that the solar system is not isolated, but part of a galactic crossroads, where material from distant stars occasionally intersects with our own. Its Mars flyby and solar encounter will be our one and only chance to study it in action, to watch as sunlight awakens a body that has traveled frozen and silent for millions of years. And when it vanishes, the data we collect will become part of a legacy that stretches far beyond a single comet. It will inform our understanding of planetary formation, galactic dynamics, and the possibility that life's ingredients may be scattered among the stars. Atlas's close approaches are not just astronomical events, they are moments of contact between worlds, fleeting, unrepeatable, and deeply profound. The saga of 3I Atlas leaves us with more than just the story of an interstellar comet streaking through the solar system at impossible speeds. It leaves us with a reminder of how vast, dynamic, and interconnected the universe truly is. This object, racing along a hyperbolic path, with an eccentricity of 6.2 and a velocity of 68 kilometers per second, has forced humanity to confront the limits of our technology, the gaps in our knowledge, and the fragility of our assumptions about the cosmos. It is easy to think of our solar system as an isolated bubble, a closed arena where planets orbit predictably and comets follow well-worn paths. But Atlas's arrival shattered that illusion. It showed us that we are part of a galactic network of debris and wanderers, fragments of other systems that occasionally sweep through our own neighborhood, bringing with them secrets older than our sun and more mysterious than anything we have created. Its discovery was a warning and an opportunity, a chance to study the chemistry and physics of an alien object, and also a reminder that for every Atlas we see, countless others may pass unnoticed. In many ways, the legacy of 3I Atlas is not just scientific but philosophical. It underscores the violence inherent in the formation of planetary systems. Atlas itself is a casualty of that violence, ejected from its home star's gravity by catastrophic interactions with massive planets, binary stars, or even the remnants of stellar explosions. Yet, in its exile, it carries a record of its birthplace, preserved in its ice, dust, and organic compounds. When sunlight struck its frozen surface and released gases into a vast coma and tail, what we were witnessing was not merely a comet coming alive, but a system billions of years gone, speaking across light years through chemistry. In every molecule of methane, every trace of carbon monoxide, there is a signature of the environment in which it was born. That is the true gift of interstellar visitors. They bring us pieces of other worlds, physical evidence that can never be gleaned from distant starlight alone. Atlas made that gift available, if only briefly, before vanishing into eternal darkness. The comet's near miss with early detection also exposed vulnerabilities that humanity cannot ignore. If a 10 to 20 kilometer wide object can remain hidden in plain sight for weeks, camouflaged by the dense star fields of Sagittarius, then what else might we be missing? Our planetary defense systems are not infallible, and Atlas was a fortunate discovery rather than the product of flawless surveillance. This has sobering implications. The sky is filled with far more than we can track, and while most of it is harmless, the gaps in detection remind us of our limitations. At the same time, these shortcomings inspire hope, because new observatories like the Vera C. Rubin Observatory will soon transform these rare chance encounters into routine detections. When the Rubin telescope begins operations, we may discover dozens of interstellar objects every decade, allowing us to compare them as a population rather than marvel at each one as an isolated anomaly. Atlas, then, is not the end, but the beginning of a new chapter in astronomy. The chapter of interstellar object science, where alien wanderers become part of regular study rather than one-time spectacles. Yet there is something profoundly moving about the fleeting nature of this encounter. Unlike comets of our solar system, which return after decades or centuries, Atlas will never pass this way again. Its hyperbolic path guarantees that once it completes its swing around the sun, it will disappear forever, vanishing into the blackness between the stars. For astronomers and ordinary people alike, this gives its passage an almost poetic quality. Here is a messenger from another system, briefly illuminated by our star, sharing its story and then gone, perhaps never to encounter another civilization in its endless journey. In that sense, Atlas is not just a scientific subject, but a cosmic reminder of impermanence. It teaches us that opportunities are fleeting, that the universe offers us rare gifts only once, and that it is up to us to seize them while they last. The conclusion of Atlas's story is also the beginning of new ambitions. Missions like ESA's Comet Interceptor, already planned for launch later this decade, may one day rendezvous with an interstellar object. Future propulsion systems, sound drives, solar sails, even nuclear propulsion could make it possible to chase down visitors like Atlas in real time, intercepting them before they vanish. The possibility of returning samples of alien material to Earth is no longer pure speculation, but a realistic scientific objective. Atlas has shown us what is possible, what is urgent and what is at stake. Its legacy will not be the months it spent in our skies, but the generations of discovery it inspires. In the end, Atlas is more than a comet. It is a cosmic refugee, a survivor of violence on a scale beyond human comprehension, a messenger carrying the fingerprints of another star system, and a mirror reflecting our own hunger to understand the universe. Its discovery proved that the galaxy is alive with wanderers, that our solar system is not isolated, but constantly intersected by travelers from other suns. It is a reminder that our efforts to explore, to build better instruments and to think beyond Earth are not just curiosities, but necessities if we are to take our place in the wider galactic story. When Atlas fades into the dark, it will carry with it the knowledge that it has changed us, leaving us with new questions, deeper humility, and greater determination to catch the next messenger that crosses our path.